So how was the quiz? Was it too easy? Actually, I was going to ask you for cotangent fit Z to show the Cauchy-Riemann condition and differentiation, but probably it may take too long for you. Also, it actually would be a pain for us to grade. So I guess the quiz problem was relatively easier for you, right? So let's start with the Cauchy-Riemann condition. So Cauchy-Riemann condition is a prerequisite for the differentiability of a complex function fz. And we say that this function is differentiable provided partial x, partial u is partial y, partial v. Partial y, partial u is minus partial x, partial v. So this is probably one of the most important set of equations for complex variable. But sometimes in terms of polar coordinate, x, y, this is theta. So what happens if sometimes this function is given in terms of r theta? So this is r. So r is square root of x square plus y square. Theta is arctangent y over x. So what if, or sometimes you can say u r x y theta x y v r x y theta x y. So either way, the function, complex function can be written as r theta, whether x through xy or through r theta. Then anybody remembers this formula for the chain rule? Probably you have learned that in your freshman class, right? So actually, this is called chain rule. Actually, it is very easy to see that. Still copying. Check. U R theta. So partial x, partial u is actually delta x goes to 0, delta x over u r x plus delta x y theta x plus delta x y minus u r x y theta x y. That's the original definition of the partial derivative with respect to x, right? But as I told you, that in mathematics you can do nothing, you don't change anything by either adding 0 or by multiplying by 1, right? So we can try plus so actually this term and this term will cancel each other, right? You subtract uxy theta x plus delta xy, and then you add the same thing. So it's basically 0, right? So this is basically plus 0. And we can check that. You can say r x plus delta x y as r x y plus delta r, theta x plus delta x y as theta x y plus delta theta, right? You can set then it becomes what? Delta x over u I plus delta theta theta minus u I theta plus delta x goes to 0, delta x u I theta plus delta theta minus u I theta. What you can do is you divide by delta r, multiply by delta r, You divide by delta theta, multiply by delta theta. Then it becomes what? Partial r, partial u, partial x, partial r, plus partial r, partial theta, partial u, partial x, partial theta, right? This is probably the most simplest way of proving or showing the chain rule. And you can do the same thing for y. So QED. My iPad is about 8 years old, so it may, I don't know how long it lasts, but any questions about chain rule? So we have all the components, partial x, partial u, partial r, partial u, partial x, partial u, partial r, partial theta, partial u, partial x, partial theta, partial y, partial v, partial r, partial u, partial y, partial r, plus partial theta, partial v, partial y, partial theta, partial y, partial u, partial r, partial u, partial y, partial r, plus partial theta, partial u, partial y, partial theta, partial x, partial v. So this is one set for the Cauchy-Riemann condition. This is partial r, partial v, partial x, partial r, partial theta, partial v, partial x, partial theta. This is for another set of Cauchy-Riemann condition. So we still need to evaluate partial x, partial r, partial x, partial theta, partial y, partial r, partial y, partial theta, right? So we still need to evaluate this polar coordinate derivative. You still need time to copy? Today will be a little bit rough, so I'm going to go as slowly as possible. And if you still think I'm going too fast, you can just tell me it's going too fast. Okay? Or you can ask me a question, either in Korean or in English. It's okay. So R theta is tangent inverse y over x. Partial x, partial r. I think we have covered briefly about differentiation, right? So, anybody remember what is dx dx to the 1/2? What happens if you differentiate the square root of x? One over square root of x, right? Two. You know why? You probably forgot. So let's say fx is x to the 1/2. fx plus delta x plus delta 1/2, right? This is x to the 1/2, 1 plus delta over x to the 1/2. And for small delta, I told you that this is roughly delta. This is what Isaac Newton did about 400 years ago. So f x plus delta minus fx over delta is 1 over delta x 1/2 1 plus delta over 2x minus x over 1/2 1 over delta 2x delta x to the 1/2 is 2 over x to the 1/2 over 1. Right? So we can apply the chain rule again that let's say g is x plus y squared, then r is g x y square root, right? So partial x partial r is according to chain rule dg dr partial x partial g, right? This is chain rule. So that is dg dg to the 1/2 partial x partial g. But this is what? We already know this, right? This is 1/2 g to the 1/2 partial x partial g. But partial x partial g is what? This is 2x because g is x squared plus y squared. So this is g to the half x r over x. This is r, this is x. So r over x is actually cosine theta. How about partial y, partial r? This is y. Likewise, partial y, partial r is r over y is sine theta. Now we have a little bit more complicated problem. I'll go slowly. About theta. Tangent inverse theta is y over x. So let's say it's hxy. Then theta is tangent h, right? So partial x, partial theta is same as before. dh, d tangent h partial x, partial h, right? Oops. You have to forget everything. I think I made a mistake. That is, theta is tangent inverse y over x, right? This is x, this is y. So same as before, h as y over x. Then tangent theta is h, right? So d theta dh is what? Anybody remembers tangent d theta d cosine theta over sine theta? We have 1 plus, actually minus cosine square theta minus sine theta, right? 1 plus tangent square theta. Or dh d theta is 1 over d theta dh is 1 plus tangent square theta over 1 is 1 plus h square xy over 1. Therefore, partial x partial theta is dh d theta partial x partial h is 1 plus h square over minus x square over y. Right? This is 1 plus y over x square over minus x square over y. Therefore, partial x partial theta is x square plus y square minus y is minus r over sine theta. On the other hand, likewise, partial y partial theta is x square plus y square over x r over cosine theta, right? So we have all the difficult calculations. So what do we have? So previously, probably I have put many formulas in just one page. Can I move on to the next topic? So we can summarize. So partial x partial r is cosine theta, right? Partial y partial r sine theta. Partial x partial theta is minus r over sine theta. Partial y partial theta is r over cosine theta. So therefore, the first Cauchy-Riemann condition, partial x, partial u, is partial r, partial u, partial x, partial r, plus partial r, partial theta, partial u, partial x, partial theta is partial r over partial u cosine theta plus 1 over r partial theta partial u minus sine theta partial y partial v is partial r partial v partial y partial r plus partial theta partial v partial y partial theta is partial r partial u sine theta plus partial v partial theta partial v r over cosine theta. So the first Cauchy-Riemann condition, partial x partial u minus partial y partial v is equal to 0, right? So that means partial r partial u minus 1 over r partial theta partial v cosine theta plus partial r partial v minus 1 over r partial theta partial u sine theta is equal to 0 for all theta. So what is the condition for a cosine theta plus b sine theta is equal to 0 for all theta? So what is the condition if you have a cosine theta plus b sine theta is equal to 0 for all theta? When theta is equal to 0, p must be 0, right? When theta is equal to pi over 2, then cosine theta is 0, so b must be 0, right? So the only condition is a and b has to be 0, right? So the Cauchy-Riemann condition for polar coordinate is the following. Partial r partial u is 1 over r partial theta partial v. Partial r partial v is minus 1 over r partial theta partial u. That's of course. Actually, we obtain the same condition for the second Cauchy-Riemann condition. So maybe you can do that as homework. That is homework for you. So maybe as an example, there's a very simple example. Can I move on? FC log C so U is R, V is theta, right? No, L and R. Or log. So partial U is 1 over R, right? 1 over R, partial theta, partial V is 1 over R. So partial R, partial U is 1 over R, partial theta, partial V. The Cauchy-Riemann condition is satisfied, right? The other condition is 0 and 0. So perhaps you can take a break for a few minutes and continue, okay? So if you look back your high school days, or middle school days, you first learned about the function, right? Then you learn how to differentiate. Then what? Then what did you learn in your high school? Integral, like function. So the next topic is complex integration. So in complex variable theory, Cauchy is very important for mathematician. So after Cauchy-Riemann condition, the next most important statement is Cauchy's integral theorem. Cauchy의 인테그랄 정리. This is region D. So if Fz is analytic in the domain D, which is encircled by closed contour C and counterclockwise. Then Fz dz equal to 0. Fz is called analytic at z equal to z, not if fz is finite, and 2 differentiable. So Cauchy integral theorem is probably one of the most important theorem. Very simple. Fz is analytic inside the domain D. D is called domain. This is called domain. Same as region. In mathematics, you call a particular region as domain or region, whatever. The domain is actually the region when the independent variable z is defined. And fz is called analytic if fz is number 1 finite, number 2 differentiable. Differentiable means Cauchy-Riemann condition is satisfied, right? CR condition is satisfied. So we are going to show this theorem. So I'll give you time to copy first. So can I move on? So F, oops. V is y, z is x plus iy, tz is therefore tx ity, right? So fz tz is actually u plus I free tx plus ity is u dx I free dx plus I u dy minus free dy. So if you put the real part and imaginary part separately, then you have u dx minus free dy plus I free dx plus u dy. Therefore, this contour integral fz dz is c. So this means counterclockwise. So we say this is clockwise, 시계 방향. This is counterclockwise, 반시계 방향. 예? 화면이 왜 안 나오지? 되나? 안 되는 거지 지금. 다시 해야죠.
다시 켜보겠습니다.
This is called Murphy's law. 머피의 법칙. Murphy's law says if something goes wrong, it will go wrong. 저기 저장을 해놔야 되겠다. 이게 엔지니어 3이지 오늘.
네.
끄고 해야 되나 보다. Now we are back to the screen. So clockwise is 시계 방향, and counterclockwise is 반시계 방향. So that means u dx minus v dy plus I v dx plus u dy. So in order to show this relationship, so we need to check whether this is 0, right? So we need to take one side step to show this. And so if you are still copy or Stokes theorem. That is, we have counterclockwise a dx plus p dy, domain partial x partial b minus partial y partial a dx dy. Let's first check this first. I'm going to prove this later, but assuming that the Stokes theorem is true, and let's check with this. So let's first check this. This first, see, u dx minus v dy. So this is A, this is B, right? So according to Stokes theorem, this must be same as domain D, partial x partial minus v minus partial y partial u. dx dy, right? Now, according to Cauchy-Riemann condition, 2 partial y partial u is minus partial x partial v, right? So this whole thing is 0, right? Because of this. Our second integral, v dx plus u dy. So this is a, this is b. So this is partial x partial u minus partial y partial v dx dy. And again, this is what? 0. Cauchy-Riemann condition, right? Assuming the Stokes theorem is true, then you can show that this real part and imaginary part are all 0, right? So therefore, if the Cauchy-Riemann condition is satisfied, then means Fz is differentiable. Therefore, it's analytic. Then this integral, cross integral, is 0 because of the Stokes theorem. So we need to show that whether the Stokes theorem is true. The next thing is to show the Stokes theorem. But I'll stay a little bit more time with this. Now go back to Stokes theorem. So we are actually making small x and y. Delta x, delta y, x, y plus delta y over 2. Here, x, y minus delta y over 2. Here is x plus delta x over 2y. This is x minus delta x over 2y. And we are going to have the following integral. 1, 2, 3, 4. So we are going to have this following: a x y dx b x y dy. So section 1 here, a x y dx plus b x y dy is actually, for pass 1, dy is equal to 0, right? So this is a x minus x y minus delta y over 2 delta x. This is AB. AB. How about section 2? 3. Three is going this way, right? So we have minus dx. Again, a dx plus p dy is minus a x y plus delta y over 2 delta x, right? So 1 is going from this 1 and 3 are in opposite direction, right? So when you integrate, you have to change the sign. So 1 plus 3 minus a x y plus delta y over 2 minus a x y delta y over 2 delta x, and the same as this, delta y over delta y, right? So this is minus partial y partial a delta x delta y. Now over 2 we have this integral 2 p dy is actually going upward plus b x y plus x, no, b x plus delta x over 2y delta y, right? How about 4? It's going down. It's the opposite direction. So this is minus b x minus delta x over 2y delta y. So 2 plus 4 is actually b x plus delta x over 2y minus b x minus delta x over 2y delta y. You divide by delta x is partial x partial b delta x delta y. So therefore, one plus 2 plus 3 plus 4, that is small integration over this dy is partial x partial b partial y partial a delta x delta y. You can approximate this as partial x partial b minus partial y partial a dx dy over small delta s. So you can generalize. Therefore, generalize any closed integral dy some domain partial x partial b partial a dx dy. So this is a very simple proof of a Stokes theorem. So now we have shown that this is always true, that cos integral theorem is also true. Let's do some simple example. Unit circle. So this is C. Can you apply cos integral theorem or not for this problem? One over z is not analytic, right? At z is equal to 0, so we cannot apply cos integral theorem. But there is a way to integrate this. We cannot apply cos integral theorem, but nevertheless, we can still calculate this integral, because on z, you can say z r exponential I theta, right? I theta. So this is theta. So dz is actually exponential I theta, I d theta is I z d theta. So dz over z is I d theta. So this integral z over dz can be transformed into this theta integral I d theta 2 pi I. Very simple, right? time to copy. Oh, how about still unit circle? Unit circle means r is equal to 1. This is our domain. When m is a positive integer, answer is obvious, right? M is positive, then c to the m is unrelated, right? Therefore, c to the m dz is 0. Because of course it's integral 0. M is negative integer, then we cannot apply the causes integral theorem, right? Because we cannot apply integral theorem because not analytic at z is equal to 0, right? So z is equal to 0 is a particular special point that we cannot apply then what? Then we have to check case by case. So same picture, say z, exponential I theta, dz, exponential I theta, I d theta, z to the m is exponential I m theta, right? So z to the m dz is exponential I m plus 1 theta d theta I. So z to the m dz is 0 to 2 pi I exponential I m plus 1 theta d theta I 0 to 2 pi cosine m plus 1 theta d theta I minus I plus I sine m plus 1 theta d theta. So when m is integer, this is always 0, right? When m is integer, sine integer theta you integrate over from 0 to 2 pi is always 0, right? How about cosine? Same, except when n is equal to minus 1. So this is actually 0, 2 pi I and n is equal to minus 1, then cosine 0 is equal to 1. Right here, right? And n is equal to minus 1, then plus 1 is 0, and cosine 0 is 1. So therefore it is 2 pi, otherwise it's always 0. Sine is always 0. So we have the following integral. You still need time? Therefore, for unit circle, c to the m dz 2 pi I delta m minus 1. This is called Kronecker delta. Delta AB is something 1, 0. A is equal to B, A not equal to B. That's Kronecker delta. And actually, in general, we can also do the same thing for some particular point and unit circle. C is a circle surrounding around C equals C naught. We have the following: Z minus C naught to the M dz is again 2 pi I delta M minus 1. So actually you can show this very simply. You can put Z as C naught plus exponential I theta. Then dz is again exponential I theta d theta I. Z minus C naught is exponential I theta. You can show that this. So maybe you can check as a homework. So let's check when cos C Augustine (1889 to 1857). So Cauchy was born in 1789 to 1857. Anybody remembers what 1789, July 14.
French Revolution.
Right, correct. So French calls that day as a date de Bastille. So Cauchy was born in the year of the French Revolution, and he made a very important discovery of cause-symmetrical theorem when he was 20, 1809. Anybody remembers 1812? Napoleon invaded Russia, right? So before 3 years before that there was the old war in Europe between France and England. And so Napoleon was trying to defend the French from the invasion from the British Armada, British Navy. And in order to do that, the important thing is, if you want to defend France from the invasion of the British fleet, what do you need to know? The major power. You have to know the type, right? Joseph Hamman. Because you have to prepare when the British will invade. They usually you have to know the type. But the tidal force is governed by the Newtonian mechanics, right? That's what the Cauchy did. That is, we have a French, there's England, there's the tidal force is governed by the gravitation between Earth and Moon. So there is a Moon. R2, right? So this is between R1 minus R2. The tidal force proportional to the distance between R1 minus R2, right? So that is square root of R1 square plus R2 square minus 2R1 R2 cosine theta. So Cauchy needed to evaluate the theta change all the time because Moon is circulating, right? So Cauchy simplified this problem by something like A plus B cosine theta over 1. Or more generally, actually square. Sorry. The force depending on the square, so you don't need this. So Cauchy simplified this tidal force formula into very simple integral. So Cauchy tried to calculate 0 to 2 pi A plus B cosine theta over d theta. This is actually tidal force. I think it will take about an hour to calculate this integral, but starting tomorrow, I think big holiday starts, so maybe I can start a little early. 내일 수요일이니까 오늘 또 일찍 들어오니까. This integral will take about an hour. So after the big holiday, it's a full moon day, right? 중추절. So one thing you learned today, and if you like to remember that the force was formulated for the theorem to evaluate the tire force of a parade or not. Defend the French against the British. 오늘은 여기까지 하고 싶습니다. 연휴 잘 보내세요.